So welcome back, everybody. We are now entering the final section of the semester, which is the high-level querying of trees. Messy data, heterogeneous, nested, and so on. Before I go ahead with this chapter, one more opportunity. Any questions? You're sure you don't have any questions? Also on Zoom? Still no questions? Okay. Sometimes the questions need to mature a little bit, or maybe you're too shy to ask and ask later. All right. So let me continue then. Where are we? We have this stack, and you see all the progress we've made. We can store data on HDFS, on S3, encode it, even though I didn't say too much about that. We have syntax, CSV, XML, JSON, data models for trees and tables, validation, XML schema, JSON, processing with MapReduce, with Spark. We can even index the data if we're not using a data lake, but we're using a proper database management system like PostgreSQL or MongoDB. We can even index the data to make the lookup super efficient. We saw data stores like MongoDB, and now we are looking into querying. By the way, I use the term data store and not database management system because a data store doesn't have all the bells and whistles of a full-fledged database management system. MongoDB, for example, does not have a query language. It has an API, it has a JavaScript and Python API to query the data, but it doesn't have a query language like SQL. And so this is the one thing that is missing, is the query language to arrive on the top level. But you see, it's amazing, everything that we've done in all these weeks. Now, why is the query language so important? That's because of data independence. That is what Edgar Code envisioned already 55 years ago in 1970, data independence. It's the idea that when I type a SQL query, and now you all know SQL, you've done the SQL brush up, you've seen it again in Spark SQL, it's a language that you need to learn just once, and then it works everywhere. It could be on top of PostgreSQL. The elephant here is just a symbol of PostgreSQL. It can be also used on top of HBase. There is something called Hive that exposes SQL-like access to HBase as a warehouse. So you can also use it on top of HBase. You can also use SQL on top of Spark. You've seen it, right? I just showed you a couple of weeks ago, and you have exercises on that. If you use data frames in Spark, then you can use SQL again. And it's always the same language. Has dialects, right? But still, it's the same language. So you see, data independence is this. It doesn't matter how it looks like physically. It's still the same language, still the same model. So this is really amazing. And so Spark, what it's going to do is convert it to RDDs, but you don't need to worry about that. It's all hidden. It does it for you. It's going to create the RDDs for you, and you don't need to worry about it. You just type select foo from input where bar foobar in your Jupyter textbook, notebook, and that's it. So again, I insist, data independence means you provide the end user with the convenience of a language that is high level and easy to learn on a high level data model in such a way that the user does not have to worry about writing some scary codes like this, because that code was written by the data engineers of Spark so that you do not need to do it, right? So this is no longer a worry for the user. The user just types this. This is the benefit of data independence. So first benefit, productivity, because the user doesn't need to write the complex code. Second benefit, performance, because the system can decide how it's the fastest to execute it. But SQL was designed for tables. It was designed for data that is normalized, that is flat records, no nested structured in the table, and no heterogeneity, meaning that you have the same type of value in every column, you don't have any extra columns. you don't have too many missing values, still can deal with a few nulls here and there if you want, so that's what it tolerates, but it was designed for tables. It wasn't designed for the kind of data we've seen with nestedness and heterogeneity. SQL was not made for that. And so the problem we have is that we do have these kind of things in big data, what you see on the right of the screen. We do have data sets that have some extra values here and there, extra JSON keys. We have missing values in some of the objects. We might have different types of values in the same keys, right? Sometimes an integer, sometimes a string, sometimes an array of strings, sometimes an array of integers, just because of a data set that was gathered over decades, and then the schema keeps changing, right? Plus, we have nested values. We might have a table in a table in a table in a table, which in JSON terms means an object in an array in an object in an array in an object in an array in an object. And that means it's nested and heterogeneous. So the problem we have is that SQL was designed for this. SQL was never designed to handle that kind of data. And now we've seen two, I would say two, I wouldn't call them eras, but maybe periods in the history of big data that I've observed over the past 20 years. There's been a first period, I would call it the NoSQL, or meaning not only SQL era, NoSQL, in which people just thought, okay, SQL is totally useless because it can only deal with this. So let's completely forget about SQL and just build our super cool APIs in JavaScript and Python and data frames and so on to handle that data. And let's not have any query languages anymore. So that was the first periods. And then there was no query language anymore. And people would just use Pandas data frames and MongoDB, JavaScript APIs, like these kind of things to deal with this data. That was period number one in history. Then there was period number two that I think started, I would say maybe 7, 8 years ago, in which people rediscovered SQL because they realized that all these APIs and Python, using Python or JavaScript and these languages to query this data is very cumbersome. And then some people rediscovered that SQL was actually not so bad after all, because SQL is very useful to write very simply a few queries on tables. And so in that second period, what people did is that they took SQL, hit it strong enough with a hammer in order to force fit it in here. And people started using SQL on top of this, just making it work, which is kind of a good idea because at least now we have a query language again, but it has its limits. Because using SQL on top of this is kind of going to work if there's a little bit of extra values, a little bit of invalid values, a little bit of nestedness. But if there's a lot of extra values, a lot of nestedness and so on, then it turns into a nightmare again, right? Because you're not using the right tool. You're basically using a hammer with nails, sorry, no, that's correct, using a hammer with nails. You're using a hammer with a screw or a screwdriver with nails. That's basically what it amounts to. So these two periods, period number one, we drop query languages, we just use APIs. Period number two, let's go ahead and use SQL. We force feed SQL on top of this. And now we are in period number three, in which people realize these two things. We need a query language, and SQL might not be a fit for this. And in period number three, people invent query languages that work on this. And we are now in period number three. The problem of period number three is that there's 30 languages that do that. So I'm waiting with impatience for period number four, in which there is one standardized and unified query language that everybody agrees on to query this. But we are not there yet. Maybe in 10 years, it's going to happen. And the goal of this lecture, after this warning that there is not yet standardized query language, that everybody agrees on. I'm going to teach you one, because even though there's 30 languages, they all look alike. And so if I teach you one, you will be prepared for when the standardized one comes, or you will be prepared to learn any one of the other 30 languages, right? Because again, they all work with the same logic. So that's the high level explanation for this lecture. So now I'm going to dive into the details, repeating a little bit to make sure it's clear. So I'm looking at nested heterogeneous data, so collections of trees, and I want a query language that works on collections of trees. As a reminder of why SQL has its limits, a first example where we have this case right here, the invalid values, is right here. We have everywhere we have an object, but here we have just a string instead of an object for the name. Another example is countries null. So here we have that instead of it being an array, we have null, or it could even be missing, but I just put it with null. And here we have an extra field, right? So that would be this here. The extra value would be number 9. And country null could be, for example, that it's missing or absent. So if you want to try to use Spark SQL or Spark SQL on top of this, you can. So you can take a hammer, hit it hard enough, and it will actually work. Spark is going to just accept it and say, okay, here's your data frame. But look at what's happening. This is in fact a string. These here are not objects. These are strings containing the serialization of an object. Right? So these are all strings. The same here. Countries, I think it's because of these. These are strings and these are arrays. This is again a string. These are not arrays. These are the string serializing an array. Right? Do you see this? So these are strings, and here you have nulls all over the place. So what's going to happen is that you might think, okay, let's use Spark SQL. So you might think, let's use Spark SQL with name.first. It will not work. Name.first, that's not an object. It's just a string that contains curly brace, space, quote, and so on. So it means that because you hit it hard enough with a hammer to get a data frame like this, now it's your problem to parse that back to JSON, cell by cell, and then write code in Python or in C++ or in JavaScript that is going to get the objects back in here. And that gets very, very, very complex, right? So this is one of the first limitations of the data frames, right? So here we are kind of stuck because that's just becoming too complex to do. Second limitation is that you can see that this becomes complex because here we have nested arrays, and you remember this explode function. So you need to use lateral views. So you can learn that. You can try to call the lateral view. Now, one lateral view, maybe two, that's kind of going to be maybe easy to understand. But when the queries become more complex and you have like 10 lateral views in there, then for a human being, it becomes very hard to understand. And again, this is because we are pushing SQL to its limits. It wasn't made for query nested data, right? So this is why you have this complex looking syntax right here. Now, another example is that we have some use cases. That's an example with the GitHub data set. It's a GitHub data set that has heterogeneous data that basically contains everything that's been done on GitHub for years and years and years. And they publish this data set, excuse me. So you might want to ask a question on, for example, the email address of the first commit of every push or something like that, and try to write it in SQL. A colleague of mine tried, Ingo Müller. He was the head TA of big data back then. This is what he came up with. This is the SQL query. It's so complex that I cannot even tell you anymore what it's doing. But in English, it's just a small sentence to explain what this is doing. This is SQL using all the clauses you can possibly come up with. Very, very complex. This here is the version with a language that is made for messy data. It's one of the 30 languages, JSONic. I co-designed it. That's the one I'm going to teach you. But you see, just a few lines as opposed to SQL. So that's how you see some of the benefits in terms of, not losing your sanity over writing very long queries. And here you see that you're iterating over all of the events. And for every event, you're looking for the top committer. So you're looking for whoever has the highest count of commits. And then you output the author, the commits by the highest committer. And that is pretty intuitive to write. I will teach you that language, of course. I already gave you a few tutorials. But again, if you had to do it in SQL, that's what you would have to come up with. Right. So that's the high-level motivation for having a language that is specifically made for messy, nested, heterogeneous data sets. That's the slide on the data set on which these queries work. It's called GitHub Archive. It's available online. You can actually download that data. We use it at the exam. We've used it in a lot of past exams. That's an example of an object in there. Every hour, new objects get created, so it keeps growing, right? So it's getting gigantic. And what you can see here is several things. First, 10% of the path, so what I call a path is, for example, type is a path, or commit author is a path, or commit SHA is a path, or repository name is a path, created at is a path. 10% of these have mixed types. 10%. So it means that for 10% of them, some objects will have an integer, some objects will have a string, and so on. So you cannot force fit it into a data frames unless it's all turned into a string. That's what's going to happen. So that's the first thing, that they have mixed types. So that would basically correspond to that breaks domain integrity, right? And then each event would have roughly 100 attributes. So attributes, that's the relational database language. That would be JSON keys, right? So the number of JSON keys in there, that would be less than 100 for every object in my huge collection. But if I look at the entire collection, there's more than 1,300 different attributes. So every object in here uses 100 attributes out of 1,300. Right? So it means there's a lot of either missing attributes or extra attributes because the objects do not look alike. They don't look all the same. Right? So you have to imagine billions of objects, terabytes of data with plenty of mismatching types for the same path and with different attributes in every object. Right? So that's what we call messy data. You might want to clean it up for machine learning, for example, or maybe you just want to query it. So that is my use case for having a query language, as I will teach you now. Now, JSONic has the same idea as SQL, that you write your query, and then it can execute in top of Spark, in top of HBase, in top of MongoDB, in top of anything. And we have this project at ETH that is called RumbleDB, that is a JSONic engine that runs on top of Spark. So it's going to use Spark RDDs, data frames, and so on, but you won't see any of that. You just need to write JSONic and that's it. So it's data independence, writing JSONic, and everything is executing smoothly on a Spark, HDFS, S3, and so on. And so the reason it works is that just like SQL, JSONic is a declarative language. You don't tell the system how to do it. You just tell what you want. It's a declarative language. It's also a functional language, again, just like SQL. It means that the language is made of expressions, additive expression, if then else expression, and so on and so on. And every expression takes some values. We call these values an instance of the model. That can be a table, that can be a collection of trees, and so on. So an expression takes some values and outputs another value, so an instance of the model. So it's a functional language because mathematicians could actually model that with mathematical function, that every expression is a mathematical function that turns values into values. So it's very mathematical. And finally, just like SQL, again, it's called set-based. It means that an instance might have plenty of values. A table, for example, has plenty of records. So every time you have a table, you can have a billion records that you're manipulating as a single instance of the model. So that is why it's called the set-based language. And it feels like a Lego game because you just need to learn the expressions. There's 37 of them, I think, in JSONic. Just like in Lego, you might have, I don't know how many kinds of pieces there are, let's say 100. And then you have plenty of copies of these 100 pieces. Then you can assemble that. It feels exactly the same way in a language like this. RumbleDB, which we are going to use in this course, can read data from S3, from HDFS, from HTTP. It can even connect to website and just download data. Can work from your local laptop, also the files on your local computer. Can you read from Azure Blob Storage, and so on. It can read many formats from all these places. It can read text, JSON, CSV, Parquet. So Parquet is the more efficient version for valid JSON, right, which stores data frames. Roots is a bit similar to Parquet, but works for high energy physics. It's used at CERN in Geneva. LibSVM is something for machine learning. So basically, all of these formats are supported. And so the vision is that JSONic is the ideal lakehouse language. Lakehouse is a buzzword that was thrown by Databricks, the maker of Spark, in 2021 at the CIDR conference. A lakehouse is kind of something that is hybrid between a data lake, where you throw your data on HDFS or on S3, hybrid with an actual database system. A warehouse. And so it's kind of everything, all the benefits of everything as a single product. And so the idea is that JSONic or language like this is ideal for that because JSONic can deal with structured data just as well as it can deal with nested heterogeneous data. What's nice about RumbleDB is that it's all been done here at ETH by plenty of contributors. So you can see all the students who have done their thesis on this, including 3, Dwij, Matteo, and Majay, who are working on it right now. So this was done by you, by your colleagues. It's free, it's open source, so everybody can download and use it. And the way I like to introduce it is that it's like a data calculator. So just like on a calculator, you can calculate with numbers, plus, multiplication, and so on. Just like ChatGPT is a text calculator, right? It calculates but generating text. In JSONic, with RumbleDB or any other engine, we calculate with JSON. So it means that this is a calculation. For example, I have an object with a key foo associated with array 3, 4, 5. Dot foo is a calculation that explores what is associated with foo, so that's the array 3.5. Brackets 1 means you access the first position in the array, so that would be 3, and 3 plus 3 is 6, right? So it looks like a calculator, except that now you can have JSON objects and arrays in the middle of that. Right? That's the idea. And so now I just need to teach you all of the expressions that this giant calculator has. That's another example of the calculator. So this is an iteration. So here you have an object and we iterate. So dot foo takes the array here. You can see that this is my object. Dot foo takes the array. This opens the array. So it opens it and extracts 3, 4, and 5. Now you iterate on 3, 4, and 5, and for each one of 3, 4, and 5, you output the value and its square. So you have 3, 4, and 5, 9, 16, 25. These are automatically converted to strings. because a key must be a string in JSON, right? So that's why the quotes. But that was calculated. There was a query that created that JSON in just these 2 lines, right? Here's another example where, so here it's just written in the shell, but we can also read it. In that case, we read from S3. So imagine that I have a repository in S3 with plenty of Parquet file. Then I can use my Parquet file function to access them. It returns billions of objects. And then I iterate on them and I call keys. This simple query can extract the unique top-level keys of a collection with trillions of records. There can be trillions of records in S3, in this Parquet directory, and this very short query will extract all of the unique keys, right? That's something you cannot do with SQL, because SQL doesn't give you the keys. You have to know the keys in order to be using SQL, right? So that's yet another example of the sort of things that you can do. And again, look at the contrast between the fact that it can be petabytes of data, but just a few lines to do it. And all the details of how this is done, and RumbleDB will use Spark, is hidden from the user. Now, there's plenty of languages out there. I'm trying to keep track. Every couple of months, some people understand we need a language, but they come up with a new one instead of looking at the existing one. So now we have this huge plethora of languages that are popping up once in a while. And yeah, hopefully it will converge at some point. I cannot teach you all of them, so I'm just going to teach you JSONic because I was involved in that one. But not today, because I see that we are approaching 10, so I will go into this. I removed a lot of slides, by the way, because since now I'm giving you the tutorials in the first weeks, and you have the textbooks and you can practice. I skimmed, I removed a lot of slides, and I'm just in the lecture, I will go on a high level through this, but you have to just open the notebook and practice JSONic to learn it, right? So I'm going to start with the data model of JSONic, and then I will cover the high level. But above all, I'm going to give you the details, the internal details of how RumbleDB implements that, because this is the cool part, how RumbleDB automatically maps JSONic to Spark data frames and RDDs and Spark SQL, depending on the query. All right. So that's pretty much it. So thank you very much, everybody, from visiting the lecture. Thank you, Zooming, for moderating. Thank you for all the questions that you have asked. Please read the textbook. Please practice. Please solve the exercises and the quizzes. The exam date is all known. We don't know the room yet. So I think it will be announced a little bit later. The TAs are working very hard on the preparation of the exam. I will tell you maybe next week or in the final week details on the exam, what to expect. We'll give you the data sets in advance, so there will be no surprise. You'll have PostgreSQL installed, you'll have PySpark installed, you'll have RumbleDB installed, so there will be no surprise with that. And the data sets very often are unchanged, so we'll give them to you in advance, so you can even practice ahead of the exam with this. So that's it. Thank you very much. Have a good day, and see you next week at 8.